next session of our discussion on atomic absorption. In the last class, we were discussing how we can produce the atoms in the ground state. So, by introducing the sample into the flame, the solution will evaporate and then the compounds will form. Compounds will subsequently melt, decompose into ions, and the ions will pick up the electrons from the flame to produce the atoms. Now, let us try to quantify some of these ideas. The ratio of number of atoms N j in an excited state J to the number of atoms in the ground state N 0 is given by this expression N j by N 0 is equal to P j by P 0 and then multiplied by e to the power of minus E j into E j divided by k t, where P j and P 0 as the statistical weights of the excited and ground states, and k is the Boltzmann constant, T is the absolute temperature, N j is the number of atoms in the excited state and N 0 is the number of atoms in the ground state. Since this equation is inversely proportional to the absolute temperature, increase in N j by N 0 with T is also exponential. This you can deduce from the nature of the equation itself. However, N j is always small compared to N 0, that means the number of electrons atoms, number of atoms in the excited state is always small compared to the number of atoms in the ground state. Therefore, we can neglect N j in that equation, in this equation N j. So, we can assume that the number of atoms in the ground state is almost independent of the energy of the excitation, that is E j, and nominal temperature of the flame, whatever it is, or maybe around 1100 to 1200 or 2000, whatever it is. So, using this expression we can determine the number of atoms in the excited state. Let us calculate the number of atoms in the cadmium excited state. So, for this the expression is n s half, it goes to electron in the n s by 2 goes to n p 3 by 2, that is the transition, and this transition occurs at 228.8 nanometers. So, this information is available from the experiments. Now, for most of the elements P j by P 0, that is the statistical probability is 3. So, we introduce these numbers into that expression, that is in this expression P j by P 0, E j and k t etcetera, we introduce into these equations, and then we know the wavelength. So, we can convert this frequency into frequency, that is frequency is c by lambda, that is 2.998 into 10 raised to 10 centimeters per second divided by 2.288 into 10 raised to minus 5 centimeter, that is the wavelength. So, we get around approximately 1.310 into 10 raised to 15 seconds inverse. Now, E j by E 0 we can calculate the energy difference that corresponds to h mu, and we know the frequency here from the previous expression. We know Planck's constant, multiply these two, you will get 6.626 into 10 raised to minus 27 erg seconds multiplied by 1.310 into 10 raised to 15 seconds, that is frequency. Now, this gives you approximately 8.682 into 10 raised to minus 12 ergs. And then N j by N 0 we can calculate using this expression, and what you see 4.5 into 10 raised to minus 11. The number of atoms in the ground state and the number of atoms in the excited state, if you take the ratio, you will get 4.5 into 10 raised to minus 11 atoms. In other words, you can say for every 10 raised to 11 atoms in the ground state, you will find 4.5 atoms in the excited state at the temperature of 2730 Kelvin. That is the temperature what we have used. That is this tells you that the number of atoms in the excited state is really very small. Out of 10 raised to 11, only 4.5 atoms you are getting, and in the excited state. So, what is the hottest flame temperature? It could be around 4000 degree Kelvin. The population of the excited atoms, even if you raise it to 4000 Kelvin, the population would be very, very small, almost negligible. Now, we can calculate similarly for other elements like sodium, potassium, cesium, etc. And I will show you a table where the temperatures of 2000, 3000 and 4000 Kelvin are used to calculate the number of atoms in the excited state, using the same expression what we have used in the previous slide. Now, if you take a look at this table, the element cesium, its resonance line, that is lambda, is 8521 nanometers, and the energy difference is 1.46 eV. At 2000 Kelvin, if you use this expression, you will get 4.4 into 10 raised to minus 4. That is, out of every 10,000 atoms, only 4.44 atoms are in the excited state. Suppose you increase it to 3000, then the order improves by about 1 unit, that is 7.24 into 10 raised to minus 3. That means, out of every 1000 atoms, you will find 7 atoms in the excited state. Suppose you increase it to 4000 Kelvin, then you will find the order still improves, and out of every 100 atoms, you will find 3 atoms in the excited state. But suppose you do the same calculation for sodium, then what happens? You take the resonance line and take the EV energy difference, and then calculate at 2000, 3000, 4000, you will find that 9.86 and 5.88 into 10 raised to minus 4 and 4.44 atoms in the excited state around 4000 Kelvin, and here it is 10 raised to minus 6, that is at 2000 Kelvin. Sodium and cesium, they are alkali metals. Suppose you go to alkaline earth metals, then the situation changes drastically. Now, here for alkali metal, alkaline earth metal calcium 4227 is the resonance line, and you will find that at 2000 degree Kelvin, Nj by N0 is of the order of about 1.21 into 10 raised to minus 7. That means, out of 10 raised to 7 atoms, you will find only 1 atom in the excited state. Improve it to 3000 degrees, 3.69 into 10 raised to minus 5, that is out of 10,000 4 atoms. Now, 4000 slightly better. Suppose you go to iron. In iron, the resonance line is at 372, and the number of atoms in the at 2000 degrees Kelvin in the excited state is only 2.29 out of 10 raised to 9 atoms. That is, out of 1 billion, you will find only 2 or 3 atoms in the excited state. At 3000, it is slightly better, which shows 1.31. Similarly, you can calculate for number of atoms, and for copper, for example, at 2000 Kelvin, out of 10 raised to 10 atoms, you will find only 5 atoms in the excited state. For magnesium, it is out of 10 raised to 11, 3 atoms, and zinc, cadmium etcetera, if you go, you will find that out of 10 raised to 15 atoms, only 7 atoms are in the excited state. So, the sum total of this table, what we can derive is basically the number of calculations which show us that the number of atoms in the excited state, whatever be the element, it is quite small in the excited state. In the ground state, they are always more in number. So, in emission, what happens? One measures the difference between the 0 signal and the sample signal. So, if you want to measure the atomic emission, first you have to get the atoms in the excited state, and we always know that using flame, the number of atoms in the excited state are of the order of few numbers, maybe about maximum 10 out of 10 raised to 15, 10 raised to 10, 11, 10 raised to 5 like that. So, in emission one measures the difference between the 0 signal, that is when there is no excitation, and the sample signal whenever we are able to excite. So, the limit of detection is governed only by the electrical noise. Now, in atomic absorption, we have to measure between the noise level of the blank and a finite signal corresponding to the element. So, the sensitivity is always governed by the noise level of the signals. Therefore, we need to find out ways how to increase the number of atoms in the excited state. Then only we will be able to get the atomic emission, and we have to find out ways and means how to provide the maximum number of atoms in the ground state. It is not the sample in solution, it is not the ions, it is not the electrons, but your sample must be converted into atoms only. That is the catch. So, what we do is we understand that free atoms do not undergo vibrational and rotational transitions. They undergo electronic transitions, this we have covered earlier. So, the excited electrons may return to the ground state by atomic emission or by atomic fluorescence or atomic absorption. This also we have covered. So, in atomic absorption spectrometry, it involves the measurement of the absorption of electromagnetic radiation by the number of atoms in the gaseous state. If the excitation is by optical radiation, the atoms absorb the radiation of definite frequency. This absorbed energy is lost subsequently in the form of heat. So, the absorption spectrum of an element consists of number of lines which appear closer and closer together and decrease in regularity in intensity until all the individual spectral lines merge together to give you one continuous spectrum. And in the absorption of sodium, for example, so far 57 absorption lines have been observed and identified their corresponding frequency or the wavelength. In contrast to absorption, the emission lines are always more numerous and they do not exhibit the same regularity of the absorption spectrum. So, this point we will have to understand, and when I show you this sodium spectrum in the next slide, you will see that the energy difference is put in as electron volts, and these are all the radiation excitations start from 3s ground state, and you will see here number of lines until they are merging together nearby in this range. And then similarly, this corresponds to 2s half, and another energy level corresponds to 3 p by 2 and 2 3 3 by 2, 2d 3 by 2, 2d s by 2, 2f s by 2 and 2f d by 2. So, you can see that number of possibilities are there for excitation from the ground state. For example, here you can see it goes straight away up to 4.5 volts and then one around 4. Here there is one, here there is one, here there is one, here. So, a number of excitations are possible for the sodium. So, how to identify each of these lines and how we try to look at identifying these lines and try to understand their spectrum. So, if the sodium vapor is excited thermally using a hot flame or electrically, terms with arbitrary n principal number and L can be obtained, that is n can be 1, 2, 3, 4 up to infinity, L can be 1, 2, 3, 4 etcetera, and the emission spectrum can contain all the emission lines starting from 3s2 to s1 half. Similarly, complex emission spectrum can be obtained for all other elements. What we mean by similarly complex emission means almost all the elements show the same figure like this. Sodium, almost all elements you can get a figure like this. Only thing is their energy differences will be different, the spectral lines and the corresponding energies will be different. So, the energy level diagram of sodium indicates the atomic absorption lines occur only for those lines which originate from the ground state of the neutral atom, because excited concentration of the atoms in the excited state is always very small. That we have seen in the previous slides when we calculated the number of atoms in the excited state. So, the line corresponding to minimum energy is called a resonance line. Since they can come, the atoms can come into resonance with optical radiation of suitable frequency. That means, the minimum energy level and the optical optical radiation, electromagnetic radiation, if it coincides, if the frequency or the energy coincides with the minimum energy of sodium excitation, then it is called as resonance energy. So, the most intense and easily excited line should be of least energy, and hence it should be having lowest frequency. This is a very simple and clear cut situation applicable only to simple elements, that is like sodium, potassium etcetera. But for transition elements, the exact resonance line and resonance spectrum, emission spectrum are much more complex, and usually they are determined by the experiments rather than theoretical calculations. So, in order to analyze a spectrum, it is necessary for us to know which spectral term corresponds to the spectral lines. This information is provided by the selection rules of LS coupling and delta J values, and they have to change by minimum 1 unit, and n is the principal quantum number which can alter at any moment by any number, by any amount. Now, we have discussed many of these terms earlier in our discussion, especially when we are discussing fluorescence etcetera. Now, again let us recapitulate our knowledge about the energy states of an electron in an atom. We will go very quickly because we have already discussed all these things, and we know that most of the electrons are defined by 4 quantum numbers n, l, m and s. The state of an electron in an atom is described by L, S and J. That means, the energy levels are described by these terms. They are capital L, S and J denoted. Now, the orbitals of an electron in any atom have shapes of s, p, d, f and g orbitals, albeit with variance in their energy levels. It is all same, for all elements. So, the magnetic number quantum number ML can assume 2 L plus 1 configurations from minus L to plus L. This also we have discussed earlier. The magnitude of the angular momentum vector is given by square root of L into L plus 1 into h by 2 pi. So, we can discuss all these numbers right now, because to understand how complex a situation can be for an emission spectrum. So, the orbital angular momentum can be square root of L into L plus 1 multiplied by h by 2 pi, that is a very standard number. Similarly, the spin angular momentum S is also quantified according to S into S plus 1 multiplied by h by 2 pi. This quantization law for spin momentum is that Sz, these are, you remember, all these things are they are all vectors, the orbital shapes and other things. So, the quantization law for spin momentum is that Sz can have half integrals of h by 2 pi, because each electron can spin only in one direction and the other one can be in opposite direction, in order to satisfy the Pauli exclusion principle, that is each electron should be identified by 4 different quantum states, that is no 2 electrons can have the same quantum number. So, they have values of plus half or minus half, that is the precision through which the electron undergoes. So, the total angular momentum J of one electron is the vector sum of L and S, that is we can have the we can add them as if they are 2 vectors. So, the total angular momentum is given by J into J plus 1. For each electron we can have a coupling, and then for J we can have the combined quantum number also. Similarly, because these two are for number of elements, number of electrons, we write single electron we write J, and total number of electrons we write capital J. So, J can have Z components defined as plus or minus J, plus or minus J minus 1, J plus 2, like that up to J half. So, when L is equal to 1 and S is equal to half, J can have values 2 1 plus 1 by 2, that is 3 by 2, or 1 minus 1 by 2, that is 1 by 2. Since J z, that is Z component, is also derived from the orbital angular momentum and spin quantum numbers, the summation of Z components gives so many states, 1 plus 1 by 2, 1 minus 1 by 2, 0 plus half, 0 minus half, like that. So many number of states for each element, for each electron in the atom. So, for p electron, the orbital and spin quantum number can combine to give a total values of J 1 by 2 into 15, where L and S reinforce, or 1 by 2 into root 3, when L and S oppose each other. These states split into doublet with slightly differing energies. That means, the combined vector will have they will have 2 different states, but they are not different by too much energy, they are very close to each other, but still they are doublets. And these doublet frequencies will be differing by a very small amount and represented as 2 p 3 by 2 or 2 p 1 by 2. Similarly, for L is equal to 2, 3, 4, etc., we get only doublets, that is 2 d 5 by 2, 2 d 3 by 2, and then if we go for still higher energy level, that is F levels, we get 2 f 7 by 2, 2 f 5 by 2, like that. We will be able to get a number of number of energy levels. So, the total number of orbital angular momentum of an atom is basically the sum of all quantized angular momenta of the individual electrons. These states are also quantized. So, the orbital angular momentum can interact with the magnetic moment due to spin. This is termed as Russell-Sanders coupling or simply LS coupling. So, the LS interaction gives multiple splitting of each term. So, the coupling scheme for heavy atoms is called as JJ coupling. So, there is only a slight difference, but the terms what we get are entirely different for simple elements, for heavy elements, and number of it depends upon the number of electrons in the outermost orbitals, etc. So, in my next slide shows you LS coupling for S and P electrons. So, the next slide shows n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n can be anything, and for L is equal to 0, L is equal to 1, I have one more column, L is equal to 2d and 3f, L is equal to 1, L is equal to 0 is S electron, 1 is P and 2 is D, 3 is F. So, for each of these we get 1 S2, S by 2, and then 2P 2 by 2, 2P 1 by 2, and then 3D 3 by 2, 3D 5 by 2, in addition to all other previous numbers. So, the number of lines keep on increasing due to LS coupling for S and P electrons, depending upon the number of principal quantum number where we decide to look for combinations of LS coupling. So, we can have different term symbols for different kinds of mixing the vector summation, that is we can have LL coupling and then SS coupling. Orbital angular momentum of electrons are added vectorially and the resulting L values are designated as capital S, capital P, capital D, capital F, etc. Similarly, SS coupling involves only the spin angular momentum of the individual electrons and they are added vectorially to give S plus S1 plus S2, S1 plus S2 minus 1, etc., until you get S1 minus S2. So, the multiplicity of the term is 2S plus 1, that is so many numbers of spectral lines are with differing energy are possible. So, now let us take a look at LS coupling, third one, that is J should be having values varying from L plus S minus 1 up to L minus S. So, this J value when we write in the spectrum, we write it to the left of the term symbol, that is 2S plus 1, etc. So, the term symbol for a particular atomic state is expressed as 2S plus 1 and you can write capital L and then J value here. Now, let us take a small example, that is we will derive the term symbols for carbon atoms, that is it is having 2p electrons. So, the structure of carbon atoms is given by 1s2, 2s2 and 2p2. So, for two equivalent electrons L1 is equal to L2 is equal to 1 and for S electrons it is S1 is equal to S2 is equal to 1 by 2. That is we are not taking into account 1s2, but only the 2s2 and 2p2 orbitals. So, for that the values are L1 L2 is equal to 1, S1 and S2 are 1 by 2. Now, we try to combine this and when we combine this we can have capital L values like 2 1 0 and capital S should be sum of the capital S should be 1 and 0. That means, when the spins are combined we get 1, spins are opposing we get 0 and then L can have values 2 L plus 1, that is 3, that is 2 1 and 0. So, the terms corresponding to these values are calculated by spin multiplicity, that is 2S plus 1. So, for S plus 1, S is equal to 1, the multiplicity is triplet, that is 3. 3 is called as triplet and for S is equal to 0, spin multiplicity is singlet, that is only 1. So, we get 6 states just by combining these energy levels, that is 3D, 3P, 3S, 1D, 1P and 1S. So, corresponding J values we can calculate. They will be having for 3D, J values will have 3, 2 and 1. So, this gives rise to 3D3, 3D2 and 3D1 states. Similarly, 3P with J values of 2, 1 and 0 gives you 3P2, 3P1 and 3P0. So, 3S electron with J is equal to 1 gives rise to 3S1. Similarly, 1D will give you 1D2, 1P will give you 1P1 and 1S will give you 1S0. That means, so many energy levels for each carbon are possible. So, the corresponding energy level, similar energy level diagram for sodium can be shown to contain 56 transition lines for sodium and 106 for lithium, 124 for potassium and 294 lines for rubidium, etc. All these things have been identified and put in the database, and all the transitions all the transitions are possible and they can be estimated, measured and put into the database. But for our purpose, what we understand is, for atomic absorption to occur, we must have the number of atoms in the ground state, and the higher energy state with the minimum energy transition is known as resonance line, and that resonance line is defined by LS coupling or JJ coupling and SS coupling, and for the calculation of the resonance line. Now, the number of lines are possible with respect to each element, that also we should remember. So, after all this, what we can do is we have to find ways how to produce the atoms in the ground state for atomic absorption to occur. Basically, what we are looking at is how to generate the atoms in the ground state, because our the purpose of our discussion is analytical science, not the spectroscopic science. But it is important for us to appreciate that number of atomic lines are possible, which can confuse one, but we should always select the resonance line with the lowest energy state, which can take the electrons from the ground state when the electromagnetic radiation is passed, and it must excite the electrons to the next higher energy level. So, that number we have already discussed, how many we can generate at different temperatures, but still the temperatures what we are talking about, even though the number of atoms in the excited states are very small, the measurement of atomic absorption is always possible, because because we measure the absorption from the ground state and the energy difference between the excited state. So, the signal corresponding to the excitation is what we are measuring in atomic absorption. Now, let us take a look at the instrumentation. How an atomic absorption spectrometer can be constructed. In my introduction talk on atomic absorption, I had discussed that single beam AC, single beam DC can be measured, single beam, the double beam AC instrument can be measured, can be constructed, etc. Now, let us take a look at the architecture of atomic absorption spectrometer. Now, my next slide shows you the basic component of the atomic absorption, and like all other instruments, here you need a source, that is here, and then you need an absorption cell where you can produce the atoms in the ground state, and then what happens from the source, radiation is passed through the absorption cell, and then you need a monochromator to separate unwanted radiations, but you are supposed to measure only the source line, the intensity of the source line after passing through the atomic absorption. And that radiation, after you separate all other radiations using a monochromator, we take it to the detector here, and this detector is connected with an amplifier to amplify the signal, and from the amplifier the signal is handled and correlated with the concentration, and then we can do some data handling, statistical analysis, etc., and then we can have a display. So, this is how the atomic absorption spectrometer should function. Now, you will be surprised to see why I have put a computer in the center. That is because nowadays the instrumentation has become so well organized that several functions of the atomic absorption, or for that matter any instrument, can be handled by the computer microprocessor. So, we can use the microprocessor to give voltage to the source and then light up the lamp, measure the absorbance, use a monochromator for adjusting the wavelength, etc., using a servo motor, and then detectors, and then take it to the detector optics, and optics can be organized and then adjusted using a micro computer, a microprocessor, and then we have a detector, amplifier, and data handling. All these tasks can be done by the computer, and this is where the atomic absorption spectrometry scores over many other equipments, because most of the functions are taken over by the microprocessor and the computer, and it leaves minimum for the practitioner to do to adjust the positions and other things, positions of the source, absorption cell, height, weight, height, length, etc. But still the chemistry, the computer cannot do anything. So, we have to understand the different kinds of the components that go into atomic absorption spectrophotometer. So, let us proceed to our discussion on the sources. So, the radiation sources we have are the hollow cathode lamps, that is one type of radiation source. This we have already discussed during our theoretical discussion, that we need radiation of only the resonance line, and the only way we can produce this radiation with enough intensity is to use a hollow cathode lamp, that is a lamp made of the same element as the analyte. Here I am showing you the hollow cathode lamp. The figure on the left shows you an actual hollow cathode lamp used in the instrument, and the figure on the right shows you the schematic diagram of a hollow cathode lamp. Here you can see that at the back side here, where my hand is pointing out, it is only the electrical connection, and this is made of glass up to the outer portion, except this portion. This is made of quartz, because the radiation coming out of a hollow cathode lamp should pass usually contains ultraviolet lines. So, if we use glass, the radiation will be absorbed by the glass. So, most of the hollow cathode lamps are constructed using a quartz window, and then here you can see that there is one anode and cathode this cathode is in the form of a ring, the middle one, and on the top there is anode, which is a sort of a filament, and then there is a glass shield completely sealed, and then put in there is a neon or argon gas filled at about 1 to 5 torrs. So, this is the basically the construction of a hollow cathode lamp. So, it actually consists of, we can define it like this: a hollow cathode lamp consists of a glass cylinder filled with an inert gas using neon or argon under a pressure of 1 to 5 torrs, into which an anode and cathode are fused. The cathode is made of the same analyte element in the form of a cylinder, and the anode is a thick wire usually made of tungsten or a nickel. Anode can be common. So, a voltage of several hundred volts is required to light the lamp. Our normal voltage in our day to day life is 230 volts. We need almost 300, 400 volts, sometimes even less, but several hundred volts is the requirement to light the hollow cathode lamp. So, the applied voltage usually generates approximately 5 to 15 milliamperes of current, and that sets up a glow discharge of the carrier gas, that is neon or argon. So, when we pass the voltage, when we apply the voltage, inside this the gas is there, and this gas starts discharging. That means, it will give you some sort of light, and the gas will ionize to give the ions, and ions will migrate towards the cathode and anode depending upon whether they are positive or negative ions. So, this is the basic process that happens in the hollow cathode lamp whenever we start operating the hollow cathode lamp. So, you take a hollow cathode lamp, fill it with neon or argon, set up a glow discharge, and the positive ions will strike the cathode and releases the atoms of the cathode material by collision. What we mean is the ions, this is your hollow cathode lamp, and then there is argon gas filled here in all the spaces, and the positive ions will strike the cathode and the negative ions will strike the anode. This is anode, negative ions, and positive ions will go and hit the cylinder. This is in the form of a cylinder, and that is cathode. This is the basic process in which the ions will come and bombard the cathode. Now, what happens when they come, when they become energetic, they will strike the cathode, and the elements, atoms in the cathode will also get energized, and they will start sputtering. That means, they come out of the system, and then they will the positive atom ions will be inside the hollow cathode cylinder, and these ions will, before they strike the anode, they will get excited. They will pick up the free electrons from the gas, ionized gas, and they will become atoms. They get excited to next higher energy level. Before they reach the electrode, due to their kinetic process, they emit the radiation and then get settled into either onto the glass or onto the cathode material. That is the basic process. So, the process is the gas, first the gas will start ionizing, it will sputter the atoms in the cathode, and from the cathode the atoms will get excited and reach the cathode in the gaseous form, and during that process they emit the radiation, that is characteristic radiation corresponding to the same element, that is the resonance line. This is what we had discussed earlier, because the atomic resonance line has to be of the order of 0.002 nanometers accuracy. So, getting back to this our discussion, the atoms contain the atoms in the excited state emit their characteristic radiation as they return to the ground state. Eventually, the metal atoms will have to diffuse back onto the cathode surface or get redeposited on the glass walls of the tube. So, many times when you start operation of an atomic absorption, you will see that you will see a mirror like substance in this region. So, these are all the atoms silver, you will see something like silver mirror in some parts of the glass, that is the place where the atoms are redepositing after their function. So, either they are deposited on the glass walls or onto the cathode itself. So, the cylindrical configuration of the cathode, the function why we should have cylindrical composition of the cathode and only wire as an anode. It is a very simple this thing, it concentrates the emitted radiation and it also enhances the possibility of redeposition onto the confined space where we have a ringed structure. So, the electrons atoms can go back onto the cathode material. There is another possibility that these radiation coming out of it will become focused. It is easy to handle from the output from a cylindrical cathode than a filament cathode. So, the efficiency of the hollow cathode lamp depends upon the geometry as well as applied voltage. That is why we make it cylindrical and we keep on playing with the applied voltage, so that higher the voltage, higher is the current and greater is the intensity of the emitted radiation. This advantage is somewhat offset by the increase in Doppler broadening. That means, if you increase the voltage indiscriminately, there will be more atoms, there will be more disordered thermal motion of the atoms and the radiation will become weak corresponding to that frequency. So, the intensity also will be much less. So, there is always a compromise when you operate the hollow cathode lamp. You should operate it at as low voltage as possible. So, after some time what happens now? The concentration, the lamp will get fatigued and the fatigued lamp will require more voltage to give you the same intensity, but it is always at the cost of the sensitivity of the determination. So, there is a great linkage between the operating voltage and the intensity. Higher the voltage, there is another problem, that is increased number of unexcited atoms. You know, we have discussed earlier that whatever is the temperature, the number of atoms in the ground state is always more compared to number of atoms in the excited state, that is of the order of few atoms out of 10 raised to 15 or something like that. Now, what happens in the gas cloud? If there are number of atoms, they are capable of absorbing the same radiation emitted by the excited atoms. Now, what we need is the excitation from the source, that is the radiation line. Now, if there are more unexcited atoms in the same gas cloud, they will absorb the radiation. So, this is known as self reversal. If you observe in your town where there are sodium lamps on the streets, you would have seen that quite often the lamps they switch on and switch off, switch on and switch off on its own, even though the current is there. So, this if you have not seen, I request you to go and observe some of these lamps, sodium vapor lamps on the or the street lamps. They will keep on absorbing the same radiation, lamp goes off, lamp extinguishes, and then again it comes on when the number of atoms becomes less. So, the electrons atoms will go back to the ground state, and then radiation again some atoms will get excited, again the lamp will switch on. This phenomenon is known as self reversal. That means, unexcited atoms will always absorb part of the radiation, and this is also used, this principle is very useful for us in the background correction also, that we will discuss later. But for the time being, we have to understand that the increased number of unexcited atoms in the gas cloud are capable of absorbing the radiation. So, this process lowers the intensity. Therefore, we have to ensure that the radiation we always operate it at the minimum voltage and optimum intensity. So, if you buy a hollow cathode lamp for atomic absorption, they will always indicate what is the optimum voltage you should operate. Sometimes as the lamp ages, you may not get the same intensity. In that case, you should increase it by 10 volts or 15 volts or slightly increased voltage to get the same intensity. Therefore, every hollow cathode lamp has got certain amount of life, that is known as shelf life. The shelf life is also indicated by the manufacturer on the life. So, that at the end of 2 years you may have to replace the lamp or something like that, and people have to follow the instructions fairly seriously to get optimum output. Now, you can construct a variety of hollow cathode lamps, because for each analyte, for cadmium you need a cadmium lamp, manganese you need a manganese lamp, iron you need iron lamp, chromium, like that you have to have a library of hollow cathode lamps if you want to work with atomic absorption. This is a cost, this adds to the cost of atomic absorption the process, where you want to determine, you have to buy. Each hollow cathode lamp costs about 25 to 30,000 rupees, and very few hollow cathode lamp manufacturers are there. So, the instrument manufacturers usually outsource the hollow cathode lamps, and then they try to modify the connectors, so that they can use the modified lamps for their purpose. So, that the applicability of a given hollow cathode lamp is suitable only for that manufacturer. So, you can construct hollow cathode lamps for most of the elements, and by suppose you use an alloy, then what happens? An alloy is basically a mixture of number of elements. So, why not make a hollow cathode lamp of an alloy? What are the advantages? The advantages are all the elements present in a hollow cathode lamp can be excited, and you can do the multi element analysis using the same source. So, that is one advantage. Another advantage is it may reduce the cost of making so many elements. So, one single hollow cathode lamp will also be able to you can choose whatever element you want if the element is there in the alloy. So, that is possible, and multi element determination is possible. So, we can use different alloys to make hollow cathode lamps, and then at least 2 to 3 elements, 5 elements you can determine using the same lamp. Now, it is not the using a multi element hollow cathode lamp can also lead to slight difficulties. That is because the most volatile element initially when you operate, all the elements will come into the gas cloud and then they will settle down. But then when settling down, the most volatile element is the one which gets excited in the next operation compared to not so volatile element. That means, one or two elements will be preferentially dominating compared to the all the alloying elements. So, one has to be slightly careful regarding the multi-element analysis if you want to use an alloy, but still commercially such systems are available. Now, let us discuss about a hollow cathode vapor discharge other source. One is hollow cathode lamp. Are there any other sources which can give this kind of radiations which we can use in atomic absorption? Now, here I am showing you a vapor discharge lamp. This is just like a mercury vapor lamp, and only thing is the vapor lamp, here are the connections, and then we have a lamp vapor deposited here, some of the element that is deposited here, and then we have the electrical connections, and then these are the electrodes, and when you operate, this is also operated under vacuum, and there is some amount of insulation is necessary, and again the windows in this range have to be of the made of quartz. So, all other this outer shield should be glass, etc., they remain the same. So, very volatile materials like mercury, thallium, zinc, alkali metals, etc., can be determined using low pressure vapor discharge lamps. These are such lamps you would have seen in your day to day life, mercury lamps, etc., in the markets, etc., they are available. They are of low cost, give high radiant intensity. They emit strongly broadened lines owing to self absorption also and self reversal also. Therefore, VDLs must be operated at highly reduced currents. However, this leads to instability of the lamp. We will continue our discussion in the next class regarding less discharge lamps. Thank you.